Hello viewers, in this video we'll see how we can train a convolutional neural network on the Cifar-100 dataset. Before training, writing codes and training the algorithm, let's learn a little bit about the Cifar-100 dataset. If you go to this link, you will find the necessary documentation for these two datasets, and you can also download the datasets from there. Cifar-10 and Cifar-100 datasets are here. Cifar-10 dataset contains 10 classes of small color images. The classes are airplane, automobile, bird, cat, and as you can see, the rest. While the Cifar-100 dataset is an extended version, it has a total of 100 classes and a total of 60,000 images. Each of the it has total 20 superclasses, of which the other classes belong. For example, if we see the flowers, the flower superclass has orchids, roses, sunflowers, tulips, etc. So it has a total of 100 classes of many living beings and real world objects. The total 60,000 images, and there are 50,000 for training and 10,000 for testing. Each of the images are 32 by 32 color images, so it has 3 channels. Okay, now we know a little bit about the dataset. Let's get to coding. First we'll import these libraries. We can manually download the dataset and then unpickle it, or there is another easiest way to do it. We can access the dataset using the Keras library. Within the Keras library, there are few datasets, and Cifar-100 is one of them. So let's start. Okay. So if you are doing this for the first time, it will take some time to download the dataset. I have already downloaded the dataset. I have tested it before. So we are downloading the Cifar-100 dataset from the Keras dataset library and dividing it into training and testing sets. In the training set, we have the X-train and Y-train, and in the testing set, we have the X-test and the Y-test. So as you can see, it has successfully been loaded. So if you want to see that what is the size of an image, we can simply type xdr. Let's say we want to see the 0 number image, or the first image in the dataset, and we want to see its shape. So you can see it's 32 by 32 and 3 channel RGB, meaning it's a color image. Okay, now the next task is we have to reshape the labels of the datasets. If you see that what is the shape of the labels, ytr.shape, you can see it's a 2D array that has 50,000 for the training and one of the columns. So we have to convert it into a single dimensional array. To do that, we have to reshape the array. If we simply run these 2 lines of codes, this will reshape both the training levels and the test levels into one dimensional array. So if we now see the shape, you can see it now has only one dimension, and that is the levels of the 50,000 images. Okay, now let's plot a few images from the dataset to see actually what classes does it contain. I am plotting 20 images. Okay, so we can see 20 images from the dataset. Each of the images are 32 by 32 pixels, and you can see it's a little blurry because the size of the image is too small, the resolution is too low. That's why it looks a little blurry. So you can see there is an elephant, a bicycle, sunflower, and this all belongs to this data set. Now it's time to prepare the dataset for training. So we have to normalize the training and testing data. To normalize it, we have to divide each component, each of the pixels of each of the images by 255. Why 255? Because we know that uh, the value range of each of the pixel is within 0 to 255, 255 maximum, because it is unsigned integer type data. That's why we're dividing it with 255, and if we run these two lines, it will normalize all of our data. This is a great advantage we get on Python. We don't have to do it manually for each of the image. It will convert the whole dataset at once. Now it's time to design the neural network, the convolutional neural network to be specific. First, we need to uh, create an object of the sequential model. As you can see, we have already imported this from the Keras library, and from Keras layers, we have imported convolutional 2D, dense layer, max pooling 2D layer, and the flattened layer. Okay, so now we will add the convolutional layers into our uh, network, neural network. So we're adding first layer. First layer is the convolutional 2D layer, and we have to specify the size of the input image. In this case, the size is input shape is 32 into 32 and 3 channels. And also we have to specify the size of the kernel, that is 2 by 2 kernel. At this point, I assume you already know the basics of convolutional neural network, what is kernel and what is convolutional layer, max pooling layer. I assume you already know about these things, and you can give the filter number equals to 32, and padding and stride are optional. You can use this according to your choice. After the convolutional layer, we're using a max pooling 2D layer. We know we use the max pooling 2D layer to reduce the dimensionality of the image. Okay, and the size of the pooling filter is also 2 by 2. Then again we are using the convolutional 2D layer, and after that the max pooling 2D layer. So we have 4 feature extraction layers. These layers are called feature extraction layer, convolutional pooling, convolutional pooling, and after that we have to flatten the image that of which the features has been extracted. After that we will add the dense layers, the hidden layers in the neural network, and we have given 256 neurons in the first dense layer. After that we have the size, and we have given 128 neurons, and at the last layer it should be the number of your classes. So in this dataset we have 100 classes. That's why we are using here 100. If you are using Cifar-10, then use 10 here. And in the dense layers we're using ReLU as the activation function, and at the final layer or the classification layer we're using softmax classifier. Softmax classifier is used to classify and predict the probability of which class the image would belong. And after that we are printing the summary of the model. Okay, let's build the neural network. Okay, so here is the summary of our model. It tells how many parameters we have to train in each layer, and as you can see, the This is our final total number of parameters that the neural network needs to be trained. Now we need to specify the model compilation parameters. First, we have to specify the what kind of loss function we will be using. In this case, we are using sparse categorical cross entropy, and after that, the optimizer would be the Adam optimizer, and the matrix that will measure the, how the model is performing. It will be the accuracy. Okay, now we can compile the model. After that, we'll train our neural network. So to train the neural network, just use the fit function, and here we are using the first argument, that is uh, the, the training images, and the second parameter is the level of the training images, and I am running this for 25 epochs. I have tried running this before, and I have got a good accuracy after 85 epochs, so I suggest to use 100 epochs here. I am reducing the number of epochs because of the shortage of time that we want to um, train this network faster. Okay, so I am putting it on training. Okay, as you can see, the training has been started. It will take 10 to 15 minutes, so we'll come back after 15 minutes. Okay, so the training is complete. As you can see, the training accuracy achieved is 92.89%, and it took about 15 minutes. So now we'll test the accuracy of the model using the remaining data, the test data. Don't get confused. This is the training accuracy, not the test accuracy. So we can get the test accuracy by evaluating the model with our remaining test data and the test levels. And if we run these two lines, you can see the training accuracy is 33.93%. This is not much expected accuracy, but you can increase the accuracy by tweaking some other parameters, like you can do some changes in the architecture of the neural network. You can add dropout, or uh, the batch layers, or the or changing some other parameters. Um, this could increase the accuracy. We can see the training accuracy was so high. This happened because of the overfitting problem, and the dropout could reduce this problem. So try on your own. uh, and we can actually also plot the confusion matrix generated. So here is the confusion matrix. So the confusion matrix for classes like 100 classes, it's hard to observe because the true positive, true negative, we cannot separate these things from here, but you can achieve the it from here. It would be much more understanding for the Cifar-10 if you try it. The confusion matrix is necessary if you want to um, describe how the classification was performed by the model. You can also derive the loss curve and the learning curve from the history generated during the model training. So this was uh, the pretty much training of the convolutional neural network on the Cifar-100 dataset. Let me know what is your accuracy on the comment below, and the code will be in the description. Thank you for watching.